Let's take a look at this example here. We have this RLC circuit with a switch that has been closed for a long time, and it's going to be open, so it's closed for a long time, and it's going to be open at t equals 0, and we want to find the initial conditions. So right after the switch is opened, here the current and the voltage. We'll look at the change in the current, the change in the voltage, and we want to look at the final as time approaches infinity. So a couple things we want to do is we want to break this circuit down into different states. So I have here listed, of course we got the original circuit. I have here listed state 1, 2, and 3, where the first circuit here is going to be t less than 0, or as the book uses, t0 minus. The second here is going to be immediately after the switch is opened, t0 plus, and then the last one is going to be at t as it reaches infinity. So those are the three states we want to come up with to get the initial and final conditions. So we're looking for essentially in this problem, we're looking at initial and final conditions or states, okay, values. Now a couple of things we want to consider and how we got these circuits is if the switch is closed for a long time before t equals 0, okay, which is what this problem is stating. So that means the circuit has reached a DC steady state. So now we have DC steady state at t equals 0. So we have DC steady state at t equals 0. And at steady state, what that means is the inductor is going to act like a short. So we have our inductor is going to be equivalent to a short, and then the capacitor is going to be equivalent to an open circuit. Okay, and the capacitor is going to behave like an open circuit. So at t equals 0 minus, we're going to have this circuit where, again, the inductor is going to be a short, and then our capacitor is going to be an open circuit. So this is our capacitor here. All right. So we can solve for this this circuit. So we have, let me scroll up here. Our current I at 0 minus is going to equal to what we have here is we have 12 over 4 plus 2. Okay, and so we have our 12 volts, so I equals V over R. So, and then the 4 ohms and the 2 ohms are going to be in series, so we just add them. So we got 12 volts over 4 plus 2, 12 over 6, and that's going to give us 2 amps. Similarly, our voltage at 0 minus is going to be 2 times I, okay, and that's what we just solved for, which was 2 amps, so it's going to be 2 times 2, it's going to give us 4 volts. So we've got those resolved at this point. So this is because we've been the switch has been closed for a long time. Okay, and since the inductor current and the capacitor current, capacitor voltage can't change abruptly. Okay, so let's go ahead. We've known this from the previous chapter. Both inductor current and capacitor voltage cannot change abruptly that means at I 0 plus, immediately after and our I 0 minus our equal, and that's going to give us our 2 amps that we just solved for. And similarly, our voltage right after the switch is made is going to be 4 volts. All right, so we'll keep those two things in mind. And now let's look at the circuit at t equals 0 plus. Okay, at t equals 0 plus, all right, that's immediately, so this is immediately after switch. Okay, and in this case, remember the problem is the switch has been closed for a long time, so now the switch is opened. So if the switch opens right here, so we have the switch that opens, what happens is you have this 4 ohms, you have this inductor, this resistor is no longer in play, and we have the capacitor. So we just have an RLC circuit, okay, with a source. Okay, so the equivalent circuit is going to be in figure B here. So the same current flows through both the inductor and the capacitor in this case. So this current is going to flow through the inductor and the capacitor. All right, so what we can now define as I sub C, let me rewrite this, I sub C 0 plus is going to equal to I 0 plus. Okay, and we already said that's going to be 2 amps. And then since C dV dt equals IC, we can rewrite this guy. We got dV over dt is equal to IC over the capacitance. Okay, and let me go ahead and scroll up just a little bit. All right, so then we can say our dV 0 plus over dt is going to equal to IC 0 plus over C, which is just 2 over, and our capacitance value here is 0.1 farad. So over 0.1, which gives us 20 volts per second. We'll keep that on the side here. And then similarly, we can do the same thing for the inductor. Similarly, we know that L di dt is equal to VL. So we can rewrite this. So we got di over dt is equal to VL over L. So now we can get VL by applying KVL. So we'll do KVL, so we can get V sub L. And if you look up here, V sub VL here is this guy. So we can just apply KVL across this circuit. So it gives us minus 12 volts, 4 times I, and we said I plus, 0 plus, plus VL, plus V, in this case V 0 plus. Okay, so let's go ahead and write that equation down. So in this case we get minus 12 plus 4 I 0 plus VL 0 plus V 0 plus, all equals to 0. We can rearrange and we get V sub L 0 plus is equal to 12 minus 8 minus 4, which equals 0. Okay, and then we can write di 0 plus over dt equals VL 0 plus over L, which is just 0 over, our L was 0.25, which is just 0 amps per second. We'll write that down here. We save that value. Okay, so now we've solved for our first state here. So we have t less than 0. We got our current there. We figured out right after the switch is made, we got dV and we got di. Okay, now let's look at, so that the question was asking for these guys. We got those, we got these. Now what we need to do is figure out our infinity, time infinity, which is that our third circuit there. Okay, so for t greater than 0, again, so this is, you can think about this again as t greater than 0. We can think of this as t goes to infinity. We get steady state again, steady state again. Okay, so the inductor acts like a short. Okay, so this inductor is going to be a short. Alright, and the capacitor, as we said before, is going to be an open circuit. And the capacitor is going to be an open circuit, which is going to be here. Okay, so the circuit in this case becomes that figure C. Okay, so when the figure C, of course, now the switch is, remember the switch was closed for a long time, the switch is open, so that's why we lose that resistor. It's no longer there. So now this is all that we have, is we have the 12 volts and the 4 ohms. So from that we can say, well, our current at infinity is just 0 amps, and our voltage at infinity is just 12 volts. And that's how we solve for this problem. Again, we break it down into the 3 stages. Before the switch is made, in this case it was closed for a long time, so you're at steady state. You can treat the inductor and the capacitor in their respective DC states. Then right after the switch is made, you're in the circuit B, and that's where you do the majority of the mathematical analysis to get the values needed there. And then as you reach infinity, you're going back to steady state again, and then the capacitor and circuits and then the inductor go back to DC state. They're going to be, the inductor will be a short circuit, and the capacitor will be in for that. We solve for that accordingly. And that's how you do this problem.